So in this video, we're going to carry out the details of what we've outlined in a previous video. We're going to trying to make our way over to double integrals in Calculus 3, but we're going to remind ourselves about Riemann's sum and the fundamental theorem of calculus from Calculus 1. So we're going to look at the function f of x is equal to x squared plus 1. And on the interval I is going from 0 to 4. Okay. Now we have a sketch of that, so we can work from there. Here's 1. Okay. And after 4 units, we're at a value of 5. Right. And so what we're trying to compute is the definite integral from 0 to 4 of x plus 1 dx. And this was a notation that we knew was going to give us the area under this curve, right? The area. And so that is the interpretation of this definite integral. The way to handle that was the way the definite integral was introduced in Calculus 1 was through something called the Riemann sum. Okay. And it required that you split the region I up into a certain number of pieces. So I'm going to start with 4 rectangles. And so if you take the interval 0 to 4, this is a to b, and you take b minus a divided by the number of rectangles n, that would give 4 divided by 4, which is equal to 1. This quantity, b minus a over n, is what we called delta x. So what we have here is that we have the interval from 0 to 4 split up into 4 different subregions. Okay? So here is our interval I going from 0 to 4 subdivided into n is equal to 4 pieces. Okay? The next thing you needed to do was to decide on which point in each of these subintervals were you going to evaluate the function at. And typically, there are typical choices here. We could choose the right endpoints, the right endpoint problem. And if you chose the right endpoints, you take 1, 2, 3, and then 4. And then you evaluate the function at each of those endpoints. Right? And then you draw a rectangle that has that height. Okay? And then we want to add up all those rectangles. So when you add up the areas of those rectangles, right, you'll have the function evaluated at 1 plus the function evaluated at 2 plus the function evaluated at 3 plus the function evaluated at 4. There are 4 of those terms, and then you need to multiply by delta x. Okay, so the function evaluated at 1, okay, is 1 plus 1. The function evaluated at 2 is 2 plus 1. The function evaluated at 3 is 3 plus 1. The function evaluated at 4 is 4 plus 1. And then our delta x is equal to 1. Now I'm going to try to show a pattern here, and this will help going forward. You see the 1, the 2, the 3, the 4. So essentially we have 1 plus 2 plus 3 plus 4, and then we have 1, 1, 2 1s, 3 1s, and then 4 1s. Okay. So now you'll notice that there is kind of a pattern going on here. Notice that n was equal to 4. That's what we started with. So this first piece here can be written in sigma notation that you're familiar with from Calculus 2. So we can sum from I going from 1 to 4 of I. That's what this part is. And then this sum can be plus adding up I going from 1 to 4 of the number 1. And then we need to multiply all that times 1. But there's an interesting quantity here, the summation, so you'll note, or you might recall, that there's this interesting summation that if you add up the numbers I going from 1 to n of I, that's 1 plus 2 plus 3 plus 4 plus keep going up to say n minus, n minus 1, and then plus up to n. You'll notice that the 1 and the n add up to n plus 1. The 2 and the n minus 1 add up to n plus 1. So really what there is that there are n plus 1s, but there are half the numbers of n of those. Okay? So what we can say here is that when you add up the numbers from 1 plus 2 plus 3 plus 4 using the formula, that you're going to get n is 4, so you'll get 4 plus 1 multiplied by 4 divided by 2. Okay? And then there is 1 plus 1 plus 1 plus 1, which is adding up the numbers I equal 1 to n of the number 1, which means that you're adding up 1 n times, which means that you'll get n. So we have 1 plus 1 plus 1 4 times, which will give us 4. Okay? And then all that will be multiplied by 1. So the answer here is going to be 5 times 4, 10 plus 4 is 14. Okay? And that's if your number of rectangles is equal to 4. Okay? What we like to do now is the general case where you take n rectangles and then take that number of rectangles going to infinity. So let's do that on the next page. So again, we're considering the function f of x is equal to x plus 1. The interval I is 0 to 4. Okay? And now instead of choosing n is equal to 4 rectangles, we would like to choose n is equal to some number of n rectangles. So delta x then is going to be b minus a divided by the number of rectangles, right? And so that's 4 over n. So now what we have is we have our interval broken up into 0 to 4 over n. We have 4 over n up to 2 times 4 over n. We have 2 times 4 over n going up to 3 times 4 over n. And this process continues until you get to n of those steps, which would be n times 4 over n. And then n minus 1 times 4 over n. Right? And so the n divided by n right here cancels and you're left with 4, and you started at 0. So now the easiest thing to do here is to choose the right endpoints. Again, let's choose right endpoints. And so what this is going to mean is that we need to evaluate our function, right, at 4 over n. We need to add that to the function evaluated at 2 times 4 over n plus the function at 3 times 4 over n, and we need to keep going until you get to the function at n times 4 over n. And those are all the heights of the rectangles, and then we need to multiply that by the width of each rectangle, which was 4 over n. Okay, so let's carry this process out. The function at 4 over n is 4 over n plus 1. The function at 2 times 4 over n is 2 times 4 over n plus 1. Plus, and you can see this process continuing until we get 2 times 4 over n plus 1. And then all that will be multiplied by 4 over n. Now we can split this just like we did before. We're going to have the summation I going from 1 to n. We can see that this is going to be I multiplied by 4 over n. plus summation I going from 1 to n of the number 1. Okay? And all of that will be multiplied by 4 over n. So now we need to compute these summations. Okay? I is the variable. I is what's changing. 4 over n is a constant, so 4 over n can come out in front of the sigma notation. And you're left with I plus summation I going from 1 to n of 1 times 4 over n. And now we get to use that handy formula that we're going to see again later in Calculus 3 part, that the summation from I going from 1 to n of I is n times n plus 1 over 2. And the summation from I going from 1 to n of 1 is equal to n. So putting all this together and applying these two formulas will lead to 4 over n times n plus 1 over 2 plus n, and all of that will be multiplied by 4 over n. And if you do a little bit of algebra here, the n's will distribute the 4 over n through. Distribute the 4 over n, the n will cancel, and you'll be left with 4 times n plus 1. Maybe I can simplify that just a little bit further. The 4 and the 2 cancel also, so we're left with 2 times n plus 1 plus 4, and all that is multiplied by 4 over n. So we will get 2n plus 2 plus 4 multiplied by 4 over n, which comes out to be, oh, sorry, let's see, 2n plus 6 times 4 over n. Distribute the 4 over n, and you will get 8 plus 24 over n. Okay. And then what happens as the number of rectangles goes to infinity, but this limit is evaluatable, so this limit, as n goes to infinity, this part will go to 0, and you're left with 8 as your answer. Okay? And so that is the Riemann sum for that definite integral. Okay. So we know that this notation, the definite integral from 0 to 4 of x plus 1 dx, if we did n going to infinity Riemann sum with right endpoints, we got 8 as our answer. But you also get the same thing, hopefully, if you do the shortcut method for the fundamental theorem of calculus, which was to first find an antiderivative of x plus 1, which is x squared over 2 plus x, and then evaluate that x squared over 2 plus x, evaluated it from 0 to 4. So you will get 4 squared over 2 plus 4 minus 0 squared over 2 plus 0. So you get 4 squared, which is 16 over 2 plus 4. Let me make sure I've done that right. 16 over 2 plus 4, that's 8 plus 4, which is equal to 12. Okay, so that's what I was supposed to get for my double integral for the Riemann sum. So maybe I left out a term. Let me go back and let me pause, and I will go back to that previous video and see if I can, the previous part. I will come back in just a second. So we're back. The little error that we made was a parentheses error right here. So here's the parentheses that I needed to take out. And so when you did the correct algebra there, the n's would cancel. You'd get 2 times n plus 2, and then this n would stick around. And that means that you would have 3n plus 2. And then when you distribute the 4 over n, you would get 12 plus 8 over n. And as n goes to infinity, the answer there is 12 as expected. So sorry, that was a parentheses error right here. But the point being that that's how the Riemann sum is done, and it is this symbol that the meaning of that symbol is a Riemann sum. It is the limit as n goes to infinity of the summation from I is equal to 1 to n of the function evaluated at a plus I times delta x multiplied by delta x. And it's this case when we're doing the a plus I delta x that we're doing right endpoints for this problem. Now there are other endpoints you can do, but I think the easiest way to write down this definite integral as a limit is as right here. So this is the Riemann sum is the idea that we're going to try to continue doing in Calculus 3.